We want to find the derivative of ln of absolute value of x. Okay? As you know, that absolute value can be written into piecewise function, eh? So we just put ln in front of those two. Good? Okay, let's do that. So I'm going to divide this into two cases because otherwise it becomes messy. Case 1, x is positive. Okay, and then case 2, x is negative. Somebody tell me why am I not considering x is equal to 0? Usually we throw the equal sign into one of the two, usually positive side. How come it's missing?
As
Undefined.
Yeah, ln, you cannot put ln 0, right? Okay, good. Now let's take a derivative of ln x then, right? Is that 1 over x? Yeah, sure. Now let's take a derivative of ln negative x. See, this is what ln absolute value of x is, right? So we are just taking it two different pieces. And that, of course, is 1 over negative x. Tell me what I'm forgetting. I'm forgetting one thing. What is it?
Chain rule.
What? Repeat that.
Chain rule.
Chain rule, that negative sign. You get it? Oh, yeah. Wait. Then that tells you this is 1 over x, okay? Actually, I'm going to write it like this. So that tells you then, of course, derivative of ln absolute value x is 1 over x, and it appears on both sides. No, really? Do you believe it? Well, I got a machine that takes the derivative for you. Okay, so here it is. I'm going to graph it. So ln, okay, absolute value of x. It of course looks like this, so obviously, right? Oh no, you don't, this is not obvious to you now, is it? Okay, whatever. I'm gonna zoom in a little bit. Okay, now plot derivative. Where's a derivative? Yeah, there's a derivative. Oh, whatever that means, right? Let's graph it. Do you recognize this? Oh my God, right? This is 1 over x now, isn't it? You get it? Okay, that was amazing. Now, then, so absolute value, even if there's an absolute value here, because usually when we say derivative of ln x, x is just positive, and then that 1 over x only appears on the right-hand side, right? This is it, because the other side doesn't even exist. But if you put absolute value around ln x, then it's the entire 1 over x. Only place that, of course, problematic is vertical asymptote right here. The function does not exist. Okay. Then, what can you tell me about the antiderivative of 1 over x? Right here. What's the antiderivative of this? It's ln absolute value of x now, isn't it? Ah, okay. Now, finally, we can get to this thing. Remember when I was teaching you about the derivative of e to the x, ln x, that kind of thing, right? Then I told you that most common definition of ln was really this. This is f of x is equal to 1 over x. And then if you start cutting from here, 1, and then right there call it x, and that area is ln x. Do you remember this talk? Shall we verify if this is true or not? Actually, this is usually the definition on most books, but now we can prove it. Because our definition was like e to the x, derivative of e to the x was e to the x. You get it? So start from 1 and x and 1 over t dt. Remember this? Okay, that, of course, what is the antiderivative of 1 over t? We just did it. ln absolute value of t from 1 to x, right? Say yes. And that is, of course, ln x, right? X being positive at the moment, minus ln 1. What is ln 1? Oh my God. What is ln 1, people?
0.
0. There. You get it? Now you see. This is like, in a way, antiderivative symbol, right? Antiderivative of 1 over something is, of course, ln. You get it? Okay, so now you've seen this proof. The other one, that 1 plus 1 over k to the k's power, limit k approaching infinity, that you have to wait until chapter 8, later part of chapter 8 to see that one. But okay, that's great. Now let's do this. Well, we just learned what the antiderivative 1 over something is, right? So we can just use it. So this is same as antiderivative. What's the antiderivative? Well, ln absolute value 2x minus 3. Now tell me what I'm forgetting, because I'm still forgetting something.
Chain rule.
Chain rule again, right? Oh, let's take a derivative. If you take a derivative, this, and you're supposed to have 2, multiply by that 2, right? So we have to compensate for that, so we put 1/2 in front. You get it? Can you think like this? Say yes. Okay, this is equal to 1/2 ln. If you plug in 12, too much arithmetics? And I'm gonna take that bracket and common factor 1/2 out. So move this thing out of the bracket. Minus ln 3. Say you're with me. Questions? Now this then becomes 1/2 of ln 9a. Too much algebra? And then, of course, this becomes ln 3a. Too much algebra? With me? Good? Okay. Smooth sailing. Now we'll do this. Okay, first of all, say, watch this. And tell me, I'm gonna screw up intentionally again, and tell me what's wrong with this. What's wrong with this?
Chain rule.
No, it's not even chain rule.
Exhibits, but right
Can't
now
have ln
they're
of a
pretty
negative.
clear to me.
If you do this,
ln isn't the antiderivative.
This is negative 10 points, okay? You've been warned, and this is on the recording. If you misuse ln like that, negative 10-point rule applies. You've been warned on the recording, so you cannot say I never told you so. Don't do it. Don't do it. Bad things happen, okay? Oh my God, no. God, no. Okay. Second try. This is how you're supposed to do it, right? Only time you get ln is if it's just 1 over x, that kind of form. You know what I'm saying? Okay, so you are supposed to add 1, so this is negative 1. And then you divide by that, so it's negative like that, eh? Say yes. Somebody point out what's wrong with this. So this now becomes Plug in 3, so this is negative 1/3 minus plug in 1, so negative 1. Oh, so we have 2/3. That's a nice answer, right? Somebody tell me what's wrong with this. This is 0 points if you do it. Why does it get 0? It looks perfectly good. Let's take out the calculator, shall we? Okay, do this with me. I wanna clear that plot. Okay, 1 over x squared, eh? You with me? Okay, I mean, we didn't have to do it like that, but hey, quit. We want to do it the fast way, not the way that impresses your study date, right? Okay, maybe we'll do both. So math, 9 is the hot key, right? That thingy. So we put negative, and negative sign and minus sign are two different things. So negative 1, go up there, and 3. And then we can put y1 now. Remember how to do y1 like that. Okay, and x here. Good. Ready? Whoops. It says divide by 0. Whatever that, what does that mean? Could we try trapezoidal approximation now? Yeah. Do you know what this thing looks like? This is why being able to feel the graph, it looks like this. There's a vertical asymptote. I'm gonna take out the fully cooked turkey right there. How are you gonna draw your trapezoid? This side is infinitely high. You know what I'm saying? This area is infinity. This is why proofs matter. When I was proving the fundamental theorem of calculus, what was the assumption? Therefore, if you don't meet that assumption, then this thing fails. What was it?
It has to be continuous.
Well, not okay, yeah. It has to be well behaved, right? This is one of the worst behavior of any function now, isn't it? Non-existing, vertical asymptote, infinity, right? And people call this singularity. You have heard that before? Singularity? This is a prime example of singularity. You get it? And it is your job to know, because I might actually trick you like this. Evaluate this, and on a multiple choice, one of the choice will be this. And if you choose that, you get nothing. It is your job to know that this function has a vertical asymptote between this number and that number. You get it? Therefore, you pick it out, because calculator knows better. So what is your answer then? What are you supposed to say? Technical word answer is this. Ooh. Divergent. Do you remember that divergence of infinite series? Because the integral is the infinite series after all, right? Sigma n approaching infinity, the limit n approaching infinity of sigma from 1 to, yeah, just divergent series. You get it? Let's do this one first. 25. 25. Don't write this down and see how many points this will earn. Oh, that must be 36 ln and 2x plus 1 cubed. How many points, children?
0.
No, it's not 0.
Negative 10.
This is negative 10 pointer, okay? Second warning in video, okay? Don't do it, don't do it. I will do it. I will give you negative 10. I've done it every single year for last dozen years at least. Every year there is one. And some years, multiple people who gets this dubious negative 10. Okay, don't do it. Okay, so that's saying no. Okay, this is how you're supposed to do it. Let's rewrite this so that it's easier for you to recognize. This is equal to 0 to 1 of 36 and 2x plus 1 negative third power. You get it? And so ln only applies when this thingy is first power in the denominator. You know what I'm saying? Okay, now I'll just write 36 here, and then this becomes 2x plus 1, and then we add 1, so this is negative 2, correct? So far so good. Now we'll adjust these numbers backward. Let's take a derivative. If you take a derivative, this negative 2 comes out, so we have to compensate for that first. You understand that? So when we take a derivative, this will cancel that, so we go back to the original state. Now, on top of that, that chain rule, this 2 will come out again. Okay? So we have to adjust one more time. Good? And from 0 to 1. Okay? Now, this is negative 9, isn't it? Negative 9. Did you know that you can just take it outside of the bracket like that? Like what? Why? It's not because it's a rule, it's a common factor. Okay, I'm going to explain on the side why that is the case. Okay? On a side, if I left it in there, this is what's the equivalent of it. I'm going to do it up here. See, if you do it this way, what ends up happening is that you plug in 1 here, right? So you have negative 9 times 1 over 9, eh? And minus, and then there's a negative 9, and then you plug in 0 here, so you get 1. So far so good? I mean, this case, it works out, but do you see this negative, this 9 is a common factor? We can factor it. I mean, you can do something like this. Then you will have 1, 9 minus 1. So that's what's going on. When I take it outside, now come back here and watch this. When I take it outside, this is usually easier arithmetics. And then you plug in 1 here, so this becomes 1 over 9. And then minus, plug in 0, that becomes 1. You see, these two are the same thing. You get it? Okay, so taking it outside, it's not just bringing it outside the bracket, it's really a common factor. So this thing means there are two terms, one with this and one with this common factor. So it's a regular algebra. And then, oh, my computer is frozen. Okay. And then this, of course, is negative 8 over 9, eh? Times 9, negative 9, so we have 8. Good question? Moving on. Okay, let's do 31. 31. Do you know what this thing looks like? Why don't I show you the picture of what this thing looks like? This thing looks like this, doesn't it? And limits of integration is from -4 to 8. So let's say, well, I don't know why I am so anal, but this thing not being exactly 45 degrees bothers me. Okay, say -4 is here, and then 8 is twice as much. Can we use triangle area to figure this out, or you want to integrate? Who's the owner of this question? I can do it either way.
Can you show both ways?
Why don't I do that, right? Okay, so this is 8. My computer. This is 8, and this is 8, right? So this is 32. Too much geometry. This length is 4, and this is 4, right? So this is 8. So our answer is 40. How about that? That's one way to do it. The other way, now let's remember this piecewise function. I'm going to write it here. This piecewise function can be rewritten like this, right? You know what I'm saying? So why don't I do this? From -4 to 0 using this piece plus 0 to 8 and x dx using that piece. You know what I'm saying? See, when I was proving the fundamental theorem, I said the function has to be well-behaved function. Well, this is not a well-behaved function, it's pointy, right? But we can get away with it by just chopping this integral into two pieces, because the integrals areas do add. This 8 and 32 will add. So these two integrals add, because the integral just means that area. You know what I'm saying? Then this is a well-behaved function, and that's a well-behaved function. And same thing applies even if you have a jump discontinuity. As long as that discontinuity is not infinite, it's fine. We can just chop it up, and then they all become well-behaved functions. You get it? So this is the beauty about integrals. Now, this one, of course, is negative, and then x squared, and then 1/2. You know what I'm saying? Now, I'm gonna, because I just showed you, conveniently put a bracket here. And this one is 1/2 and x squared from 0 to 8. You know what I'm saying? Now 0 minus, right? Maybe I should write it. We have 0 minus negative 1/2 times 16. You know what I'm saying? Which is 8, that 8. And then plus 1/2, and then 8 squared, which is 64, minus 0. You get it? Which is 32. So together, they give you 40. I like geometric ways so much better. You know what I'm saying? That is if you can feel the graph, which is a key skill in calculus for this kind of reasons. Questions before I move on to number 40? Nay? Okay, then let's do number 40 then. Number 40 is here, and let me bring it down just a little bit. Okay. Short way or the long way? Or both? Let's do both, because we got nothing better to do today. Okay, let's predict. This, we want the derivative of this, right? So dy over dx. If you take a derivative of this is an integral function. This integral itself is an outside function, and that is the inside function, correct? So according to fundamental theorem, if you take a derivative of the integral, they cancel, and that thingy, which is the argument of the function, goes into t. So far, so good. So what we are gonna have is square root, space, 2 plus cosine q, and instead of t, we put 7x squared. Good? Are you with me? And then chain rule applies to that thingy, so we have 14x. Good? Now, if you didn't get this, let's do it the long way to figure the whole thing out. So long way is here. dy over dx is equal to, well, before we do dy over dx, shall we just evaluate this integral? How do I want to say it? Yeah, I'll just do it this way. Okay, so d over dx, and then I can evaluate this integral. Well, we can't because we don't know what the antiderivative of this is. We'll just call it capital F. From 2 to 7x squared, and then we'll specify what capital F means, where df dt means square root of this little function. That means capital F is the antiderivative of that thing inside. So far with me? Okay, now this is the derivative of, now we plug it in. So we plug in this thingy in, so we have f of 7x squared minus, and then plug in 2, so we have f of 2. You with me? You with me? Now we take a derivative. Somebody had a question? Okay, we take a derivative, so derivative f is this, correct? So that thingy is right here, except inside we don't have a t, we have 7x squared, so I substituted 7x squared for t. You with me? And then chain rule applies with this inside function, which is out here. Then most common question is, what happened to this? Well, this is a constant, so when you take a derivative, it dies. So we just have this. You get it? And I'm going to delete this thing. How about that? Are we good?
Yeah, thank you.
Okay, then we have number 46, which is a beauty. God, I love integral function, okay? Now, when I say I love this, it means something else. It's not like I fell in love with integral function, right? I already live with my love of my life, okay, for the record. Now, f, let's try to sketch this function f, shall we? Yeah. So let's say this is your y-axis. And then let's say we have an x-axis somewhere here. Okay. Now this function f, now I'm going to sketch f, has a positive derivative, meaning it's increasing everywhere. You get it? And then it passes through 1, 0. So whatever this function is, it's going to look like this. This is graph of f. And then it does pass through 1, 0 here. You with me? Okay, now, actually it doesn't mean it's ends there. It could continue on forever. Okay. Now this g of x is an integral function of f, antiderivative with a big initial value 0. What's the other way of saying this? Is then that means g prime of x is equal to, according to fundamental theorem, f of x, isn't it? All this thingy, if you take a derivative, cancels, and that x goes in instead of t. Good? So this f of x also is a g prime of x. Good? Now, we can answer the question. G is differentiable. Yeah, here's a derivative everywhere. Good? G is continuous function of f. Yeah, sure, because you have something like this already, right? This is continuous function, and if you take an integral of that, of course it gives you continuous function. For the record, and then you may not know this, even if we have a jump discontinuity, integral function is still continuous because you're adding this infinitely thin width of rectangles at a time. So it increases infinitesimal. So it's always continuous. Get it? Only time you may have a problem is if you have vertical asymptotes. That runs into a problem. But other than that, jump discontinuity, as you've seen it in this problem, this is not jump, but integral doesn't care. Even if this is jump, we can chop it up and add them up, and they still add. Okay? Now, so yes, this is continuous. Now, graph of G has a horizontal tangent. Is that true? Yeah, because C, I'm going to answer C here. Because G prime of 1, which is f of 1, which is 0, that means it's flat. You get it? Okay. G has a local minimum. Yeah, well, I misread it. It has a local maximum. Of course not. Let's look at the sign chart here. This is negative, right? And this is positive, meaning G changes from decreasing to increasing. So this is your minimum, isn't it? So nope, this is false. And this is true, it's a minimum. Get it? Decreasing to increasing. Okay, now F, graph of G has an inflection point. Nope, how do we know that? Because this is an answer justification for F. G double prime of X, which is same as F prime of X now, isn't it? And this is increasing everywhere. This is positive everywhere, right? They actually tell you it's a positive derivative always. This is always positive, meaning G is concave up. You get it? No point of inflection right here. Good? Okay, now graph of dg dx, which is equal to f, crosses x-axis at 1. Yeah, sure it does right there. You get it? Because that's what you're told as a given. So that's true. How about that? Are we good? Question? So we want to know if h of x defined like this is increasing or decreasing from 1 to 5, right? Okay. So first of all, h prime of x, according to product rule, is f prime of x, g of x, and plus f of x, g prime of x, right? And then we need to know whether this is positive or negative now, right? Okay. So f prime of x is this, right? This is always positive. So 1 through 5, do you see that this quantity is positive? Right. So what we know, I'm going to do it on the side here. F prime of x is positive on 1 through 5. That much is great. Now, what about g? G prime of x. G is decreasing from here to here, right? Which tells you g prime of x. Oh, did I put another prime? G prime of x is negative on this same interval. So far, so good. So far, so good. Okay, so that's nice. So we'll make our, so this is positive, right? Okay, and then we know this is negative. So far, so good. Okay, what about g of x? G of x from 1 through 5 is negative, isn't it? By looking at it. So this is negative. Now, this is not showing your work. I'm just trying to explain what's going on, right? And then only thing is this, right? Is this positive or negative? Well, we have to get it out of this information we have, okay? So let's just think about it here. I'm running out of space, so I'm going to write it on this corner right here. This is a big deal, this concept. what happens if we take a derivative of f prime of x, let's say, not as an x, but let's put t, dt from 1 through 5. What does that give you? Well, according to fundamental theorem of calculus, that gives you f of 5, yeah, f of 5 minus f of 1. So far, so good? Right, you kind of see where this is going because f of 1 is already 3, right? Right, and this is increasing everywhere. So this is positive everywhere. So we are adding positive area. However, now I can do one better, and there's a reason that I put t here. So instead of this 5, erase it. And then what happens if I put x there? I have created f of x with my favorite integral function. So now we can say f of x is equal to f of 1 plus 1 through x of f prime of t dt. So far, so good. Now, let's say this is positive already, right? This is 3. So I'm gonna plug in 3 now. So what we have is 3 plus some kind of integral function, f prime of t dt. So far, so good. But now we can say f prime of x is positive, right? So whatever thingy that we are integrating, this gives you a positive area, and we are adding 3. So do you see then, run out of space. So I'm gonna go sideways. So do you see that f of x, it has to be positive, at least from 1 through 3. Actually, this is a bracket. That makes sense to you? We are starting with positive number 3, and we are adding positive area to it. Right? Because this is always fun. Yes.
But can you just since you know f prime of f of 1 is positive, and you know f prime is always increasing at least after 1. So can you just conclude that f of x, as long as x is greater than 1, then you know it's positive. Is that what you're trying to do?
You just summarized what I was saying. I would take that kind of reason. Okay. This is a more like mathematical, very professional type of paragraph. But we are saying exactly the same thing, and I will, if you summarize it well, I will take that on the test.
Okay, thank you. And sorry, I'm wondering, what's the question asking again?
Oh, is h increasing or decreasing during interval 1 through 5?
Oh, okay, thank you.
So now we know this is positive, right? Do you see that the entire quantity h prime of x must be negative now? So we have positive times negative plus positive times negative, right? Okay, this itself is not showing the work, but this is good enough with all of this other information. You know what I'm saying? So now we can say h prime of x is negative on 1 through 5. Therefore, h is decreasing. You get it? You see, conveniently, I did not write the interval and left it there because if I want to write it, then it has to be bracket, which I don't want to mess with. So it's just like, this is still a loophole, right? Because this is a true statement. Derivative is negative and decreasing, and that's all I said. And then these people at AP will take it. I don't want to write down any statement that's not true. Any questions before I move on to number 42, was it? Okay, let's move on to, recording is going rather well. So it was just the third period. Okay, let's do this 42. Okay, this 42. There are two ways of doing it, and I'm going to show you both. Number one, just a long regular way. See, if you want to take dy over dx, which is the derivative of this integral thingy, right? Uh-oh, see, this happened. This happened at least a dozen times today. Okay, Matthew, do you have a question while I try to revive OneNote?
Yes. Is it alright if I ask you?
This computer is trying to.
Okay, my question is, will there be any proof for the Riemann sum? Can you hear me clearly?
No, I can't.
Do you hear me?
Slightly better.
I think it's on my mic echoing.
Okay.
Okay. Will there be any proof
You're still
of the
breaking up.
Riemann sum in the test?
Riemann sum? And answer to that is maybe. Nice try. Okay, we're back. Hopefully we can finish this recording. Oh, now there are two of them. Okay, this is x here and 2x here. And we have 1 over t squared plus 1 dt. Okay, option number, see, this thing just becomes this thingy, t 2x in here, and the chain rule if this is just constant, but this x messes you up, right? So there are two schools of thought. One of them is this. And let's just call it f of t. From x to 2x, where df dt is equal to this thingy. So this thing tells you that capital F is the antiderivative of this. Oh, by the way, this antiderivative does exist. It happens to be inverse tangent. I know you don't recognize it because I told you not to memorize any of that formula, so you should not recognize it, but this is antiderivative. I mean, derivative of inverse tangent. I'm going to teach you how to figure that out in chapter 6. There's a whole section on it, so wait until then. But we'll just call it F, okay? Then we substitute it. So 2x in, so we have becomes f of 2x minus f of x. You with me so far? Okay, now we take a derivative. So the first one, df dt, which is this, right? However, the chain rule of 2x, so we change that numerator to 2. Doesn't want to erase? Erase.